At the heart of a distant galaxy lies Holmberg 15A, a black hole so massive it defies imagination. It swallows stars, bends light, and challenges everything we know about gravity itself. Tonight we'll explore this cosmic colossus and the secrets it hides. If you enjoy the wonders of deep space, please like, subscribe, and share. And tell us in the comments, what would you ask a black hole if it could answer? Thank you for watching. Now, let's begin. Holmberg 15A lies at the center of the Ab85 cluster, a vast congregation of galaxies suspended in a silent web of gravity. From afar it appears like a dim haze against the black of intergalactic space, an enormous form so diffuse that its light almost disappears into the dark. Yet this faint glow marks one of the largest known elliptical galaxies in the universe, an immense stellar system that stretches hundreds of thousands of light-years from edge to edge. Its surface brightness is so low that it can seem nearly invisible, a soft blur where light and space blend. Seen through long exposures, the luminous fog thickens toward the middle, fading so gently outward that the boundary between galaxy and void is uncertain. Here brightness is deceptive. The true measure of its scale lies in gravity, not in glow. The giant elliptical sits among hundreds of companions, bound together within the Ab85 cluster. These surrounding galaxies trace long orbits through the shared gravitational basin, moving slowly over cosmic timescales. The cluster itself spans millions of light-years, but this central member anchors its structure. Around it, smaller galaxies drift like embers, each one caught within the invisible field that extends far beyond visible light. Over billions of years, this gravitational architecture has drawn matter inward, merging systems and building the massive core that defines the cluster today. In that quiet assembly, Holmberg 15A stands as both the heart and the memory of all that came before. At the outermost edge, the galaxy's halo becomes a faint veil of stars. Long exposures reveal streams and shells, remnants of galaxies it absorbed in the distant past. These outskirts are almost ethereal, lit by red and yellow stars spread thinly through an enormous volume. Many of them were torn from smaller galaxies that ventured too close, their orbits stretched and mixed by the tidal pull of this gravitational colossus. In that region, time moves slowly. Stars wander through arcs so large that one orbit could last longer than the universe itself. The light there is weak but ancient, a whisper of collisions long resolved. Closer toward the center, the diffuse structure grows more uniform. The host galaxy contains little dust and almost no cool gas. It is composed primarily of old, stable stars that have burned for billions of years. These are not the brilliant blue stars of a youthful spiral galaxy, but the quiet red suns of a mature one. The absence of fresh gas means that few new stars can form. In visible wavelengths, the giant glows softly amber, while in the infrared it shows a more even warm tone. Ultraviolet images confirm its stillness. No bursts, no streaks, no sign of recent creation. The light of the entire system is a sum of age. Within that calm glow lies immense mass. The total stellar population is thought to number in the trillions, but their combined light is spread so broadly that the surface appears dim. If the Milky Way were placed inside this vast sphere, its spiral arms would vanish deep within the inner halo. A single orbit for a star on the outer rim could take tens of billions of years, an interval beyond any familiar measure. Each point of light contributes to a gravitational field that dominates the cluster around it. This field is not a sharp force, but a gentle pull that extends outward, holding smaller galaxies in wide slow motion. The central giant was first catalogued in the mid-20th century, when astronomers began mapping rich galaxy clusters. early photographs showed a diffuse glow unlike typical ellipticals. Later observations with more sensitive instruments revealed its immense size and confirmed it as a seedy galaxy, the designation for the largest, most centrally dominant ellipticals found in clusters. The C stands for central, the D for diffuse. Over time, systems like this grow through mergers, each collision adding new layers of stars and extending the halo further. Holmberg 15A, shaped by countless such events, is the accumulated outcome of many galaxies' quiet erasure. The surrounding environment amplifies this impression of scale. Between galaxies in the cluster lies a thin atmosphere of hot gas that emits X-rays, a relic of ancient star formation and supernova explosions. This intracluster medium glows faintly heated to millions of degrees, filling the space between galaxies with an invisible fog. The central colossus sits immersed in that gas, its gravity compressing and shaping the temperature gradients around it. Through this medium, smaller galaxies fall slowly inward, losing energy as they merge with the central body, adding still more stars to its halo. At its core, the galaxy's light profile flattens rather than peaks, a subtle clue that something massive and unseen dominates within. Instead of brightening sharply toward the center, it spreads out, a sign that stars once orbiting there were ejected by powerful gravitational encounters. This deficit region may mark the aftermath of collisions between supermassive black holes during ancient mergers. Even without direct evidence, the structure implies an extraordinary central mass, one far greater than most galaxies contain. Later observations would confirm that suspicion, revealing the presence of one of the largest black holes ever detected. But in this first view, the evidence rests quietly in shape and shadow. Across the electromagnetic spectrum, the giant elliptical presents different faces. Optical and infrared images show its soft, continuous light. X-ray observations capture the glowing cluster gas surrounding it. Radio data hint at long-faded jets, relics of past energetic activity near its center. Combined, these signals describe a galaxy that has reached a kind of equilibrium, old, enormous, and nearly still. Every wavelength contributes a different perspective on the same enduring quiet, a gravitational monument built from many others now resting in cosmic calm. Seen from Earth, the galaxy's glow is faint, its light dispersed across the black field of space. Yet every photon gathered from it began its journey when life on Earth was still primitive. The light now entering telescopes left that system more than 700 million years ago, carrying the memory of a universe younger than ours. As astronomers collect those ancient signals, they reconstruct a portrait not of motion, but of endurance, a massive quiescent giant holding its shape through time. In this way, Holmberg 15A, the central mass of Abell 85, stands as both record and relic, its dim light, preserving the quiet grandeur of a universe that has aged but never truly rested. The Abell 85 cluster spreads across millions of light years, a congregation of galaxies drawn together by the long arm of gravity. Within this realm, the giant at its center exerts a steady influence, shaping orbits and quieting motion over cosmic time. The cluster lies hundreds of millions of light-years from Earth, and though light from its members reaches us faintly, it carries the outline of an immense structure, a bound collection of matter formed not in isolation, but through the gathering of many ancient fragments. Around the central colossus, dozens of galaxies drift in gentle arcs, each tracing paths so vast that even the speed of light seems slow against them. Gravity here is not a violent force, but a soft, persistent sculpting form through endurance rather than eruption. When astronomers observe Abell 85, they see a snapshot of equilibrium, the energy of expansion countered by the deep pull of accumulated mass. The cluster's galaxies vary in size and brightness, yet all share a faint kinship in their movement. Smaller ellipticals and lenticulars linger closer to the middle, while spiral systems appear mostly along the outskirts, where the cluster's gravitational grip weakens. These spirals, with their arms of dust and gas, often arrive from the surrounding cosmic web, long filaments of matter, connecting clusters across the universe. As they fall inward, the environment strips them of material, converting them slowly into duller, smoother forms. Over time, the process leaves a population dominated by old gas-poor galaxies. Abell 85, like other mature clusters, has reached this quiet stage. Star formation within it has slowed dramatically. The cluster glows mostly with the light of red ancient stars, their collective radiance filtered through the faint haze of intra-cluster gas. This gas fills the space between galaxies, an invisible medium that only reveals itself through X-rays. It is hot beyond any earthly scale, reaching tens of millions of degrees, and so diffuse that it could not be felt even if one could drift among its atoms. Yet its combined mass exceeds that of all the stars in the cluster. The gas forms a continuous envelope that defines the cluster's atmosphere. Within it, galaxies move like fish in a vast sea, leaving behind wakes of stripped material. When a smaller system plunges toward the center, it encounters resistance, losing gas and stars to the larger body. Over billions of years, such encounters contribute to the growth of the central elliptical, feeding it with fragments of stellar systems long dissolved. The result is a slow accretion, a steady gathering that transforms the center into the massive host observed today. The gravitational field of the cluster extends far beyond the visible galaxies. It includes not only stars and gas, but also the invisible mass known as dark matter. This unseen component provides most of the binding energy holding Abell 85 together. Without it, the galaxies would drift apart under the universe's expansion. Instead, they remain connected, orbiting within a potential well, carved by dark matter halos overlapping and merging over cosmic time. Mapping this structure requires indirect observation. Astronomers measure the motions of the galaxies and the temperature of the X-ray gas to infer the distribution of mass. From these data, they reconstruct a portrait of the cluster as a colossal three-dimensional web of gravity-luminous matter embedded in a framework of the unseen. Holmberg 15A, positioned at the bottom of this gravitational basin, occupies the region of highest density. It sits not just at the center of light, but at the very focus of the cluster's invisible architecture. Within this gravitational environment, energy circulates in slow balance. The intracluster gas emits radiation as it cools, but the central regions remain hot, suggesting that some process continually replenishes that energy. Astronomers suspect that active galactic nuclei, the energetic cores of galaxies powered by supermassive black holes, inject energy back into the gas through jets and outflows. In Abell 85, traces of this process linger as faint radio emissions and subtle cavities, in the X-ray maps likely remnants of earlier activity from the core of the central galaxy. Such feedback prevents the gas from cooling too quickly, stabilizing the cluster's structure. Over billions of years, this quiet exchange of energy maintains equilibrium between collapse and expansion, between silence and motion. Seen across different wavelengths, Abell 85 reveals its layered composition. In visible light, the cluster appears as a field of small pale points, densely packed toward the center. In X-ray imagery, the gas forms a diffuse glow surrounding the heart of the system, with slight ripples marking temperature variations. Infrared surveys detect the warmth of older stars, while radio observations trace the faint signatures of magnetic fields threading through the hot gas. Each band of observation contributes another dimension, showing a complex environment bound by gravity yet alive with subtle motion. The entire structure represents a stage in cosmic evolution where growth has slowed but not ceased a mature system, maintaining its form through the quiet work of balance. The dynamics of the cluster evolve slowly, but its history reaches back to the earliest epochs of galaxy formation. Billions of years ago, when the universe was denser and smaller proto-galaxies merged along cosmic filaments, gathering into groups that later combined into clusters like this one. During that time, collisions were frequent and energetic, driving bursts of star formation and feeding the growth of black holes. As time passed, these violent interactions gave way to a more ordered state. The large ellipticals at the centers of clusters, including the massive body-dominating Abel 85, are the products of those ancient encounters. Their current stillness is not emptiness, but the aftermath of long activity, a phase of slow consolidation following ages of chaos. For astronomers, Abel 85 serves as both a laboratory and a relic. It illustrates how gravity sculpts matter on the grandest scales, how small structures combine to form immense ones, and how the energy released in those processes shapes the evolution of galaxies. Every galaxy within the cluster carries part of this story, some as survivors of mergers, others as newcomers falling inward for the first time. The central colossus, however, is the record keeper, its smooth light encoding the accumulated past. The stars within it move through orbits shaped not by single events, but by the combined pull of the entire cluster. Each motion is a thread in a cosmic weave, a pattern that will persist for billions of years more. From Earth's perspective, the cluster appears motionless, a fixed arrangement of faint lights. Yet deep exposures reveal its richness, arcs of distorted galaxies in the background bent by gravitational lensing, faint tails of stripped gas stretching between members, and the diffuse glow of intra-cluster light, created by stars no longer bound to any single home. Together they form a portrait of quiet grandeur, a place where time accumulates like sediment, and where even silence has weight. In this vast, slow-moving congregation, the central galaxy holds its position as the anchor of the cluster's structure. Around it, matter continues to fall inward, and though the process unfolds beyond human timescales, its outcome is certain: the continued growth of the central mass, the deepening of the cluster's gravitational well, and the persistence of balance in a universe that rarely rests. Holmberg 15A surrounds itself with a halo so faint that even powerful telescopes must gather light for hours before it becomes visible. This vast envelope extends far beyond the bright core, a diffuse sphere of ancient starlight fading gradually into the darkness of intergalactic space. The stars that inhabit this halo are remnants of long histories, survivors of collisions, mergers, and gravitational tides that have slowly drawn matter inward from the cluster around it. To see this halo is to look at the aftermath of time itself, for it records every encounter that built the galaxy's immense form. The halo's light is weak, less than 1% of the brightness of a spiral galaxy's disk, yet it dominates in size, reaching hundreds of thousands of light years into the surrounding void. Its glow is smooth and continuous, not defined by edges or boundaries, as if the galaxy has dissolved gently into the darkness that holds it. Within this faint region, stars drift far apart, sometimes separated by distances that would span entire galaxies elsewhere. Their motion is slow, guided not by local gravity, but by the overall pull of the central mass. In deep optical images, this outer sphere resembles a mist of light, a dim fog that encircles the brighter core. Long tidal streams trace faint arcs through it, vestiges of smaller galaxies long absorbed. These streams form patterns like ripples frozen in time, curving around the center in wide orbits, that will take billions of years to complete. Some of the light within the halo may not even belong to Holmberg 15A alone, but to the intra-cluster medium stars that drift freely through the gravitational field of Able 85 unbound to any single system. Their combined glow adds to the soft radiance that envelops the cluster's center, blending seamlessly with the galaxy's own light. In this way, the halo becomes a shared property of the cluster itself, a luminous sea connecting its largest members. The composition of this halo reveals the outcome of long evolution. Spectroscopic studies show that its stars are old and metal-rich, meaning they formed in earlier generations of galaxies before being stripped and merged into this collective envelope. The abundance of heavy elements indicates that they have lived through multiple cycles of star birth and death. Supernovae from ancient epochs scattered carbon, oxygen, and iron through the interstellar medium, enriching future stars. Over cosmic time, those materials gathered again, carried into Holmberg 15A through mergers and tidal interactions. The result is a vast population of stars whose age exceeds 10 billion years, their light soft and red, their lives quiet and enduring. Unlike the thin active disks of spiral galaxies, the halo of this giant elliptical shows no sign of new formation. It is a monument to what once was light from suns that have burned for eons in an environment where little now changes. At such distances from the core, gravity acts gently. A single orbit may require times longer than the age of the universe, meaning that much of the halo has not yet completed a single revolution since its formation. The stars drift almost freely, tracing the shape of the galaxy's gravitational potential. They're bound yet only loosely. Some follow elongated trajectories that carry them deep into the cluster, before returning, blending the borders between one system and another. This interplay between the galaxy and its environment defines the boundary of Holmberg 15A not as a line, but as a gradual transition. The farther outward one looks, the less clear it becomes where the galaxy ends and the cluster begins. The light simply thins, fading until it merges with the diffuse glow of intergalactic space. For astronomers, measuring this halo is a delicate task. The brightness is so low that even the faintest glow of Earth's atmosphere can obscure it. Observations often rely on high-altitude or space-based telescopes where the darkness of the cosmos is undisturbed. Long exposures are stacked and combined, revealing faint gradients of light invisible in shorter views. Through these methods, researchers trace the halo's profile, mapping how its brightness decreases outward. They find that the decline is slower than in smaller ellipticals, confirming that Holmberg 15A's outer regions extend far beyond what its visible brightness would suggest. This slow fall-off in luminosity is a hallmark of seedy galaxies, whose halos are swollen by the accumulation of stars from countless mergers. The halo structure also provides clues to the galaxy's mass distribution. Stars in the outer regions move under the influence of both visible and dark matter. Their velocities, measured through subtle shifts in spectral lines, reveal how gravity changes with distance from the center. In Holmberg 15A, the pattern suggests an immense halo of dark matter, enveloping the luminous one, extending still farther into space. This invisible mass ensures that even the most distant stars remain bound, preventing them from drifting away into the cluster. The combination of visible and dark matter forms a balanced system light, tracing the surface gravity shaping the depth. At the limits of detection, the faint light of the halo becomes indistinguishable from the diffuse glow produced by stars stripped from other galaxies. This intracluster light, as it is called, is a signature of violent encounters that have long since ended. Every star in that population was once part of a smaller system, drawn out by tidal forces and left to wander. In clusters like Able 85, the fraction of total light belonging to this free-floating component can reach significant levels, showing how deeply connected the member galaxies are. In Holmberg 15A, this mingling is especially pronounced. The galaxy's enormous reach means that its halo and the cluster's background light overlap almost completely. To look at one is to see the other. Such diffuse structures change only on the grandest timescales. As the cluster continues to evolve, more galaxies will merge, more stars will be scattered into the outer regions, and the halo will grow even larger. Yet this process unfolds so slowly that for billions of years it will appear unchanged. The stars will continue their silent orbits, their light spreading thinly across space, recording the history of interactions long past. In a sense, the halo is the memory of the cluster, a luminous record that preserves the traces of everything that has ever collided here. From Earth, when viewed through the largest telescopes, the halo of Holmberg 15A challenges perception. It is not a sharp feature, but an impression, a gentle gradient of light that demands patience to discern. The eye cannot see it directly. It must be revealed through accumulation, through the steady gathering of photons over time. This patient observation mirrors the process that formed it. Slow, persistent, and cumulative. The halo is not merely a shell of stars, but a symbol of the way galaxies grow, by absorbing, by merging, by quietly blending their light into something larger than themselves. And as the photons from that far-flung halo continue their journey toward us, crossing hundreds of millions of light-years, they carry with them the calm testimony of endurance light from the most tenuous edge of a colossal structure, drifting through the endless dark toward the instruments and eyes that wait to receive it. Far from the bright core of Holmberg 15A, where light thins into near darkness, lies a region of gentle gradients and drifting stars. The outskirts of the galaxy are neither fully within nor entirely beyond its grasp. They are a transitional space where the last bound stars stretch into the cluster's wider field, and where the gravity of the central mass competes with that of neighbouring galaxies. In this domain, the density of stars is so low that an observer could travel for thousands of light-years without passing near another sun. Yet despite this sparseness, the region remains part of the same slow dance, a continuation of the galaxy's reach shaped by billions of years of quiet interactions. Here the motions of stars trace the aftermath of ancient collisions, forming patterns that record the galaxy's gradual growth from countless smaller bodies. These outskirts are faint but not featureless. In long exposures, faint shells and arcs of light appear delicate as breath against the black. They are remnants of galaxies once drawn into the giant's pull, their stars stretched along orbits before settling into the broader halo. Each faint ripple of light marks an event long concluded, a merger that ended quietly as the smaller companion dissolved into the greater mass. The stars within these structures now move on paths determined by the combined gravity of the entire system, blending slowly into the background. Their orbits are vast and elongated, looping far beyond the central regions before curving back again. Over time, their patterns will fade, erased by random motions and the slow diffusion of stellar light. Yet in this moment they stand as soft reminders of how even immense galaxies are built through accretion, the patient gathering of fragments over cosmic time. In the outermost zones, gravity weakens but never disappears. The balance between the galaxy's hold and the cluster's broader pull defines the limits of what belongs to Holmberg 15A. Beyond that invisible boundary, stars drift freely through the intracluster medium, becoming part of the diffuse population that fills the space between galaxies. Within it, the edges of gravitational domains overlap, blending the identities of neighbouring systems. In such regions, there are no clear borders, only gradients of influence. A star in this area may one day fall toward the central colossus, or it may wander outward toward another member of the cluster drawn subtly by the collective field. This constant exchange gives the outskirts their living quality. They are not static peripheries, but transitional currents, part of an endless cycle of capture and release. The faint light of the outskirts carries information about the galaxy's history. Astronomers study its color and brightness to infer the ages and metallicities of its stars. The outer stars tend to be older and poorer in heavy elements, suggesting that many were drawn from smaller primitive galaxies that formed early in the universe. Their chemical simplicity contrasts with the more enriched populations near the center, where star formation once occurred more vigorously. By comparing these gradients, scientists reconstruct the sequence of growth, small ancient systems merging first, followed by larger, more evolved galaxies later. Holmberg 15A, like other central ellipticals, grew from the inside outward, expanding layer by layer, as it absorbed material over billions of years. Its outskirts, faint and extended, are the newest additions, even if the stars within them are among the oldest. Beyond the visible stars lies the extended domain of dark matter. Though unseen, it defines the shape and extent of the entire system. The stars in the outskirts move too rapidly to be held by visible matter alone, implying the presence of a vast invisible halo enveloping the galaxy. This dark component stretches even farther than the luminous one binding the outer regions and maintaining their slow rotation. Its gravitational influence acts as the unseen skeleton upon which the luminous body rests. Without it, the outskirts would disperse into the cluster, their stars lost to the surrounding void. Instead, they remain bound, moving in orbits too vast for human imagination, each star completing only a fraction of its path since the galaxy's formation. The environment around Holmberg 15A also shapes these outer zones. The intracluster medium through which the galaxy moves exerts a subtle drag, stripping away any remaining gas and smoothing the distribution of matter. Over time, this process has left the outskirts clean and quiet, devoid of cold clouds or dust. The absence of interstellar material gives the region its clarity. The light that reaches telescopes is purely stellar, unfiltered by absorption or reflection. In X-ray maps, the cluster's gas appears brightest near the center, outlining the gravitational well into which all surrounding matter is drawn. The outskirts of the giant lie embedded in that glowing medium, their faint starlight passing through a sea of ionized particles heated to millions of degrees. Within this environment, new interactions continue, though, at an almost imperceptible pace. Small galaxies still fall toward the cluster's center, occasionally passing near the outskirts of the giant elliptical. When they do, tidal forces stretch them into long filaments, stripping their stars and feeding the outer halo. These minor mergers are too slow to see unfold, but their traces appear as narrow streaks of light and faint plumes extending from the edges of the main body. Each is another contribution to the ongoing accumulation that defines the life of a central galaxy. Even when the collisions cease, the evidence of their passage lingers for billions of years in the outskirts, a faint living map of the galaxy's continuing growth. Observing such delicate features requires precision and patience. Astronomers rely on instruments that can detect differences in brightness smaller than 1,000th of the night sky's glow. By stacking exposures taken over many nights, they reveal the faint arcs and gradients that define these remote regions. These observations confirm that Holmberg 15A's outskirts are exceptionally extended, reaching farther than almost any known elliptical galaxy. The total radius where its light can still be measured surpasses 500,000 light-years, making it one of the most diffuse yet massive structures ever observed. Such size suggests an extraordinary history of mergers consistent with its role as the dominant galaxy in a rich cluster. At the edges, light becomes memory. The photons that reach telescopes today began their journey when the solar system was still forming. In that time, the stars that emitted them have barely moved their slow orbits, frozen in the vast stillness of cosmic time. The outskirts preserve that stillness. There are no shocks, no rapid changes, only the steady glow of old stars drifting through space. To look at them is to see duration itself, the lingering aftermath of creation stretched thin across distance. Every faint trace of light in those regions represents a sum of histories, each star a survivor of collisions older than our world. And yet, for all its remoteness, the outskirts of Holmberg 15A are not an end but a bridge. They connect the galaxy to the wider cluster, blending the boundary between the individual and the collective. Through them, the gravitational field of the cluster reaches inward, and through them the light of the galaxy reaches outward, joining the faint glow that fills intergalactic space. In this balance, the giant's edges speak of continuity, a reminder that in the universe, even isolation is never complete, and even the faintest light belongs to something larger than itself. The enormous mass of Holmberg 15A did not arise in isolation. It was built through countless collisions, each one erasing the structure of a smaller galaxy and folding its light into the greater whole. Deep within the faint outskirts and subtle gradients of its halo lie the relics of those ancient encounters. The galaxy's present calm conceals a long and violent history, one written not in explosions but in the slow rearrangement of gravity, light, and time. When two galaxies meet, their stars do not collide directly. Instead, their combined gravitational fields pull and stretch each other, creating long tidal streams that curl like ribbons through space. Over millions of years, these streams fade and merge, their distinct identities lost. What remains is a smooth envelope of light, a memory dissolved into structure. Holmberg 15A is the cumulative result of many such unions, a body shaped by the quiet persistence of merger after merger, until nothing of the individual remains, only the collective. Astronomers can still trace faint echoes of these collisions in the galaxy's outer halo. Deep imaging reveals shell-like arcs and loops that ripple outward from the center. These structures are fossil imprints of past interactions, the leftover choreography of gravitational encounters. Each one marks the trajectory of a smaller system that once spiraled inward, slowed by friction within the dense cluster environment. As it fell, the smaller galaxy was stretched and fragmented, its stars scattered along curved orbits. Over time, the debris wrapped around the core, forming concentric layers that now appear as subtle ripples of light. The shapes of these shells, their spacing brightness and curvature, tell scientists how many mergers occurred and how long ago. In Holmberg 15A, the large number of overlapping shells suggests a complex and prolonged assembly, likely involving both major and minor mergers, extending over billions of years. Simulations of such interactions show that when two large galaxies collide, the resulting object becomes rounder and smoother, its internal motions randomized. Stars that once orbited in orderly disks are flung into new paths, creating the isotropic distribution typical of ellipticals. The central velocity dispersion, a measure of how fast stars move in random directions, increases, and with it the galaxy's gravitational binding. Each collision adds mass to the core, driving it toward greater equilibrium. Over time, as more systems merge, the remnants lose any remaining structure or asymmetry. This is how giant ellipticals like Holmberg 15A come to exist, not through steady growth or gentle accumulation, but through the violent erasure of smaller forms until only a diffuse massive spheroid remains. the evidence of such a past is not limited to light. The chemical composition of the galaxy's stars also carries the imprint of merging. Stars from smaller, less evolved systems tend to have lower metallicities, fewer heavy elements forged in earlier generations of supernovae. When they are absorbed into a larger host, they enrich its outer regions with older, simpler stars. This creates a gradient in composition. The central stars are more metal-rich, the outer ones more primitive. Holmberg 15A shows precisely this pattern, confirming that it has swallowed numerous small companions over cosmic time. These gradual mergers, though individually minor, collectively built the enormous halo that now surrounds the central body. Each one left behind chemical traces invisible to the eye but measurable in light. Major collisions involving galaxies of comparable mass left deeper scars. During such events, central black holes from each galaxy spiral toward one another, eventually merging and releasing energy into the surrounding stars. The gravitational recoil from these processes may have ejected some stars from the very core, creating the flat central profile now observed. The absence of a strong peak in brightness, the so-called core deficit, points to this history. Stars once near the center were cast outward as the merging black holes exchange momentum. The result is a core that appears unusually large and diffuse an empty space carved by forces too immense for the eye to see. Though the direct evidence of these violent moments has long since faded, the motions of the surviving stars preserve the memory. Observations of their velocities reveal subtle asymmetries and kinematic twist signatures of orbits that have not yet fully settled. Even after billions of years, the stars still carry the imprints of the directions from which their progenitors arrived. In this sense, the galaxy is a living archive. Its overall calm masks a hidden complexity, a faint turbulence beneath the stillness, a motion too slow for human perception, but written clearly in the patterns of stellar light. The environment of Abel 85 ensured that such encounters were inevitable. Within dense clusters, galaxies rarely live in isolation. They move through the same gravitational field, crossing paths again and again as they orbit the cluster's center. Over time, these interactions drain energy from smaller systems, causing them to sink toward the middle. The process known as dynamical friction gradually transfers momentum from galaxies to the cluster's dark matter halo. Once close enough, the smaller systems are consumed by the central giant, their stars becoming part of its halo, their gas and dust dispersed into the intracluster medium. Holmberg 15A's enormous size reflects this long history of cannibalism, the cumulative capture of dozens, perhaps hundreds of smaller companions. When viewed in deep composite images, the galaxy's periphery still glows with uneven brightness, suggesting areas where material has only recently settled. These irregularities mark the latest arrivals, dwarf galaxies torn apart before their orbits could circularize. In time, even these traces will fade, smoothed by the random motions of stars and the pull of gravity. Yet for now they stand as the last visible ghosts of collision, thin veils of light marking the slow digestion of matter. In X-ray observations, corresponding enhancements in the surrounding gas temperature hint at shocks from older interactions, remnants of the energy released when galaxies merged and their interstellar media collided. The process of galactic merging is slow, but its effects are profound. It transforms not only structure, but also destiny. Each encounter redistributes energy, increases entropy, and moves the system toward a more stable, less active state. Star formation ceases as gas is heated and expelled, leaving behind a quiescent stellar population. Over billions of years, the once violent collisions lead to calm. The central colossus now sits in that stillness, its light even and unchanging. but every photon it emits carries within it the story of turmoil resolved. The galaxy's smoothness is not the absence of history, it is its completion. From Earth, the evidence of these long-ago events reaches us as faint variations in brightness across an image field. To the unaided eye, Holmberg 15A looks featureless, but under careful analysis its structure reveals an almost geological record of cosmic time. Each layer of stars, each gradient of colour, each subtle ripple in brightness, corresponds to a chapter of collision and assimilation. The galaxy's vast mass and apparent serenity are the end products of chaos transformed into order of motion reduced to balance. What remains today is a monument to endurance, a structure that has absorbed the energy of countless others, and now rests immense and silent at the centre of its cluster. In the quiet of deep space where light travels for hundreds of millions of years to reach us, those ancient collisions still echo faintly in the patterns of the giant's glow. Though the turbulence is long past, its memory endures, scattered across the faintest reaches of the galaxy's light. The calm exterior of Holmberg 15A is thus not an image of peace but of completion, the silence left. After creation's long storm has passed, the still reflection of a universe that has learned through time and gravity how to become still. The calm surface of Holmberg 15A conceals a world of movement. Every star within its enormous body follows an orbit shaped by the combined gravity of billions of others, weaving a silent choreography that has continued for eons. Though the galaxy appears static in telescopic images, its interior is alive with motion stars travelling in every direction, crossing paths without collision, tracing the gravitational signature of the colossal mass at its core. In smaller galaxies, such motions form patterns, spirals, disks, or bars that give structure to their light. But in a massive elliptical like this, order dissolves into statistical balance. The stars no longer follow organized routes. They move in all orientations, forming a vast sphere of motion governed only by gravity's symmetry. Seen as a whole, this random dance becomes stability-chaos transformed into equilibrium. Astronomers measure these movements through the Doppler shifts in starlight. When light from one side of the galaxy is slightly redshifted and the other side blue-shifted, it reveals rotation. Yet in Holmberg, 15A rotation is minimal. Instead, the dominant motion is velocity dispersion, the random speeds of countless stars moving in every direction. This dispersion reaches hundreds of kilometers per second, indicating the immense gravitational potential of the galaxy. The higher the random motion, the deeper the gravitational well. By measuring it, scientists estimate the total mass enclosed within the visible structure, including the unseen dark matter that surrounds it. In Holmberg 15A, these calculations confirm a staggering weight, one of the largest ever derived for a single galaxy. The stars act as traces of gravity, their motion translating invisible forces into observable effect. Near the center, the stars move fastest. Their orbits bend sharply around the galaxy's hidden core, following paths distorted by the presence of an enormous unseen mass. This region, only a fraction of the total diameter, dominates the dynamics of everything around it. As one moves outward, the speeds decrease but never fall to zero. Even at the edge of the luminous halo, stars continue to drift under the faint but persistent pull of the central gravity. The transition from fast inner orbits to slow outer ones defines the shape of the galaxy's potential field, revealing how matter, both visible and dark, is distributed within it. Through careful measurement of this profile, astronomers can reconstruct the architecture of the entire system without ever seeing its components directly. The flow of stellar motion within the giant follows a logic of its own. Some stars travel on nearly circular orbits, others on elongated ellipses that carry them deep into the interior before sending them back toward the edges. Many follow trajectories tilted at random angles, forming a three-dimensional lattice of movement that fills the entire volume. Over time, these paths intersect and overlap, creating a distribution that appears uniform when viewed in aggregate. This dynamic equilibrium ensures the galaxy's stability. Without it, the system would collapse inward or disperse outward. Instead, it endures balance between kinetic energy and gravity's binding pull. The random motion of individual stars is what prevents the whole from falling into its center, the same principle that keeps planets from spiraling into their suns, multiplied across trillions of orbits. In smaller galaxies, stellar motion can produce waves bars or other transient features, but in Holmberg 15A, such disturbances are suppressed by scale. Its enormous mass damps oscillations before they can grow. Any perturbation caused by a minor merger or passing object is absorbed almost instantly relative to cosmic time distributed across the collective motion of billions of stars. The result is remarkable steadiness. The velocity field within the galaxy is smooth and symmetrical, showing no significant rotation or large-scale asymmetry. Even when viewed through high-resolution spectroscopy, the motions appear isotropic, the same in every direction. This uniformity is not absence but resolution, the outcome of countless random motions averaged into stillness. Occasionally the data reveal faint deviations, small regions where the velocity field twists slightly, or where dispersion changes by a few percent. These could be remnants of past mergers' subtle scars in the galaxy's internal kinematics. They remind observers that even a system as immense as this retains faint memories of its construction. Yet the overall pattern remains one of harmony. In the language of celestial mechanics, the galaxy has reached virial equilibrium, a state where potential and kinetic energies balance perfectly, ensuring long-term stability. This balance is achieved only after billions of years of gravitational interactions, collisions, and relaxation. Holmberg 15A has had time enough to find it. In this equilibrium, individual stars experience a kind of ordered randomness. They move freely their orbits determined by the smooth potential of the entire galaxy, rather than by close encounters. The distances between them are so vast that direct collisions are virtually impossible. A star may travel for the lifetime of the universe without ever approaching another within a meaningful distance. The system's apparent density when viewed from afar is misleading. It is an illusion of scale. Inside space is mostly empty, and motion unfolds in near silence. The only true collisions here are gravitational influences exchanged at a distance, shaping paths but never touching. The diffuse nature of the galaxy amplifies this stillness. The outer regions where light fades into the intracluster medium move almost imperceptibly. The stars there are like distant satellites tracing wide arcs whose completion would take longer than the age of the cosmos. Each one contributes only a fraction of a percent to the total gravitational pull, yet together they define the slow breathing of the halo. The motions of these outer stars form the bridge between the galaxy and the surrounding cluster. They respond both to the central mass and to the gravitational tides of neighboring systems. In this overlapping domain, stellar motion becomes a measure of cosmic geography, mapping the gradual transition between one gravitational domain and another. The observation of these motions requires instruments of great precision. Telescopes equipped with integral field spectrographs capture the light from hundreds of small regions across the galaxy, measuring the tiny shifts in wavelength that reveal the direction and speed of stellar movement. The resulting data produce velocity maps, color-coded portraits of motion that replace images of static brightness with dynamic flow. In Holmberg 15A, these maps show a soft gradient near the center, evidence of slight rotation, and a broad field of random dispersion elsewhere. Together, they portray a system governed more by depth than by spin, a gravitational field so massive that even smaller symmetries vanish into symmetry. This smoothness gives the galaxy its visual serenity. Every point of light we see is an average of countless moving sources, their paths blending into uniform radiance. The galaxy's calm appearance is thus not stillness, but balance motion so vast and varied that it becomes invisible. Beneath its quiet glow lies energy beyond reckoning, the kinetic energy of trillions of stars, each one hurtling through space at hundreds of kilometers per second. Yet there is no sound, no shock, no friction, only the soft translation of motion into light, the conversion of gravity into shape. In the larger picture, the internal dynamics of Holmberg 15A link the past to the present. The random orbits are the final stage of a process that began with chaos, collisions, mergers and disruptions that scattered stars into every direction. Over billions of years, those chaotic motions settled into balance. The galaxy now exists in that calm aftermath, its internal energy dispersed but conserved. The stars move endlessly, yet their collective form remains unchanged. In this way, Holmberg 15A embodies the universe's tendency toward equilibrium, a vast, luminous sphere where disorder has matured into constancy. From Earth we see only the glow, but hidden within it is a ceaseless silent movement, a harmony of countless paths crossing in darkness, guided by gravity alone, continuing forever, as the galaxy drifts in the wider stillness of the cluster it commands. Deep within the vast and diffuse body of Holmberg 15A lies a region where light begins to bend, and where the gravity of unseen mass defines every motion. For most of cosmic history, this heart remained unknown, concealed by distance and the limits of observation. In visible light, the core appears smooth, without dust lanes or spiral structure, only a gradual brightening that fades toward the center. Yet when astronomers began to peer deeper, using infrared and radio instruments, the illusion of uniformity gave way to evidence of something extraordinary. The light from the innermost stars moves faster than theory predicts, curving around an invisible force that dominates the center. The core of this galaxy, though faint to the eye, is the site of immense gravity, a realm where matter folds inward and time itself seems to slow. Infrared observations, which can penetrate the dense stellar glow that blinds optical views, reveal a steep gradient in brightness near the core. Stars there are packed more tightly than anywhere else in the system, and their combined light glows with a reddish warmth, the signature of old suns moving at extreme speed. But even their combined mass cannot explain the depth of the gravitational well implied by their motion. The data suggest an unseen presence, one far more massive than all the stars near it combined. It is not visible directly. It does not emit or reflect light. Its influence is known only by how it shapes the motion of everything around it. The hidden heart of Holmberg 15A, long suspected, begins to emerge as the evidence of a supermassive black hole becomes impossible to ignore. In radio wavelengths, the quiet glow of synchrotron emission traces the faint signatures of ancient activity. Although Holmberg 15A is largely inactive today, low-level radio sources at its center hint at a history of accretion, the process by which matter falling into a black hole heats and radiates energy before disappearing. These faint emissions, spread across a few thousand light-years, mark the presence of a central engine that once fed more actively. Compared with the violent jets of quasars or blazars, this galaxy's nucleus is now calm, but its past is written in the faint radio haze that drifts outward from the core. The subdued signal suggests that the black hole, while enormous, now rests in a state of near dormancy, consuming little but commanding all. In X-rays, the core tells another story. Observations by space-based telescopes reveal diffuse emission from hot gas surrounding the central region. The temperature of this gas reaches tens of millions of degrees, heated by shocks and compression within the deep gravitational potential. Some of this energy may come from earlier outbursts of the central black hole, when jets and winds expelled matter into the surrounding medium. The faint X-ray glow acts as a lingering echo of those energetic times preserved in the structure of the intracluster gas. Though the activity has subsided, its imprint remains subtle: cavities, faint arcs and gradients in temperature marking where energy once flowed outward from the nucleus. The transition from the bright stellar envelope to the hidden gravitational domain is gradual but profound. Within a few thousand light-years of the center, the density of stars rises sharply, and their orbits become increasingly influenced by the invisible mass at the heart. Each star follows a curved path determined not only by the collective gravity of its neighbors, but by a deeper force pulling inward. The closer a star approaches the center, the faster it moves, and at some threshold the velocity becomes too great to be sustained by the stellar mass alone. This region, where orbital speeds rise beyond expectation, defines the gravitational sphere of influence of the central object. It is here that the galaxy's true ruler reveals itself, not through visibility but through motion. High-resolution spectroscopy has allowed astronomers to map this region in detail. By measuring the broadening of absorption lines in starlight, they infer the velocities of stars along the line of sight. The results show a steep rise toward the core consistent with the presence of a black hole, weighing tens of billions of solar masses. Such a figure places Holmberg 15A among the most massive galaxies known, its nucleus one of the largest black holes ever measured. The precision of these estimates depends on complex modeling, but the trend is unmistakable. The deeper into the core one looks, the greater the gravitational pull becomes. In this way, observation transforms into revelation. A hidden mass once inferred now emerges as a defining reality. The discovery of such enormity reshapes understanding of galaxy evolution. Supermassive black holes are known to inhabit the centers of most large galaxies, but few reach the colossal proportions of this one. Its size implies a history of repeated mergers, not only of stars and gas, but of black holes themselves. Each galactic collision that built Holmberg 15A likely brought its own central black hole, which then sank toward the middle through dynamical friction. Over time they merged, releasing gravitational waves and ejecting stars while growing still larger. The present core is the product of this sequence, a black hole forged from the union of many others. The surrounding stars moving in random orbits bear silent witness to the immense energies once released there. Despite the power contained within it, the core today is calm. The accretion rate, the amount of matter falling into the black hole, appears to be very low. The galaxy's gas reserves were long ago depleted or heated beyond the ability to cool and feed the nucleus. As a result, the central black hole now rests in a quiescent phase, shining only faintly through weak radio and X-ray emission. The surrounding stars move as they always have, their light unaffected except by gravity. To the eye, nothing marks the center but the slight brightening of stellar density. Only through careful analysis can its presence be known. This calmness, however, is deceptive. Even in dormancy, the black hole governs the structure and fate of its host, its mass-shaping orbits. Out to thousands of light years, its influence woven into the motion of every star in the core. At this depth, the concept of center takes on new meaning. There is no solid surface, no physical boundary marking where the galaxy ends and the black hole begins. Instead, there is a gradient of light and gravity, a smooth transition from the collective pull of trillions of stars to the singular force of one object. If the galaxy was stripped away, the black hole would still remain an anchor of curvature in the fabric of space-time. In that sense, the heart of Holmberg 15A is less a location than a condition, a place where matter and energy obey different rules, where space folds into itself, and where the idea of rest becomes indistinguishable from motion. From Earth, this realm cannot be seen directly. The black hole's event horizon is far too small and distant to resolve, hidden behind the luminous veil of the galaxy's core. Yet its presence is undeniable. It shapes everything around it, from the motions of stars to the temperature of gas and the distribution of light. The hidden core emerges not as a structure, but as an influence revealed through what it causes rather than what it shows. It is the silent architect of the galaxy's equilibrium, the unseen center, that gives shape to all that surrounds it. Holmberg 15A, in all its vast stillness, owes its calm to the gravity that rules its heart, a force invisible yet absolute, binding light, time, and matter into the quiet dominion of the cosmos. At the heart of Holmberg 15A, gravity dominates all things. It is not a visible force, not a beam or wind or flow, but an ever-present curvature of space that governs every motion within the galaxy. Here near the center, its influence becomes absolute. The stars move not as individuals, but as instruments of a single gravitational field that bends their paths into quiet precision. Even light itself feels this dominance, curving subtly as it escapes the deep potential well of the central mass. To an outside observer, the core seems serene, a smooth gradient of brightness. But within that calm lies a gravitational dominion of extraordinary power, one that extends across hundreds of thousands of light years and holds billions of suns in its invisible grip. The galaxy is not merely bound by this force, it is defined by it. The dominance of gravity shapes the very geometry of Holmberg 15A. Unlike spiral galaxies, which form disks through the angular momentum of rotating gas, this elliptical giant displays no such structure. Its formation history erased any coherent spin, leaving instead a three-dimensional symmetry determined entirely by gravitational equilibrium. The stars follow orbits distributed in all directions, creating a spheroidal shape whose smoothness reflects the depth of the central potential. The greater the mass at the core, the rounder the system becomes as random motion replaces ordered rotation. Thus the shape of Holmberg 15A is not a surface feature, but a direct manifestation of gravity's supremacy. The galaxy's contours are those of a gravitational well, sculpted by time mergers and the weight of invisible matter concentrated in its nucleus. Astronomers describe this inner region through models of gravitational potential. Each model attempts to reproduce the observed velocities of stars and the distribution of light by adjusting the mass of both visible and dark components. In Holmberg 15A, these models converge on an extraordinary conclusion. The central black hole alone accounts for tens of billions of solar masses, making it one of the most massive singularities known. Its gravitational reach extends across thousands of light years, influencing even stars that appear far from the center. Beyond that lies the combined gravity of the galaxy's stellar population and dark matter halo, together forming a structure so vast that even the outer halo remains bound. Within this hierarchy, the black hole is the innermost core of gravity, the deepest point in a well that spans the entire cluster. The effects of this concentration are measurable. Near the core, the gravitational field is steep, causing stellar velocities to rise dramatically. Spectroscopic measurements show stars moving at speeds of several hundred kilometers per second, their light stretched and compressed by the Doppler effect. This random motion sustains the galaxy's structure against collapse-balancing kinetic energy, against gravitational pull. Farther out, the potential flattens and velocities fall, gradually reflecting the combined influence of the surrounding halo. Every orbit, every trajectory, is a compromise between motion and the curvature of space imposed by mass. The system behaves as a single dynamic entity, its equilibrium maintained by gravity alone. Such a gravitational regime produces phenomena beyond the stellar domain. The hot gas permeating the cluster is shaped by the same potential, forming a roughly spherical atmosphere centered on the galaxy. In X-ray maps, this gas appears as a diffuse glow, extending millions of light-years, its temperature highest near the core. The gravitational well of Holmberg 15A compresses this gas, heating it to tens of millions of degrees and preventing it from cooling into new stars. Thus, gravity itself regulates the galaxy's evolution, determining not only motion, but destiny. The same force that binds the stars also suppresses the conditions for new creation, locking the system into its present quiet state. Occasionally, this gravitational dominance becomes visible through lensing, the bending of light from background galaxies passing behind the cluster. The curvature caused by the total mass of Able 85, with Holmberg 15A at its center, distorts distant sources into faint arcs and stretched smears. These optical distortions provide independent confirmation of the cluster's immense mass. By measuring their shape, astronomers can estimate how gravity is distributed, revealing that most of it is dark and invisible. Holmberg 15A sits at the deepest point of this lens, the central anchor in a network of curved space that extends far beyond its visible borders. Within the galaxy, gravitational dominance also governs the behavior of time. Near the central black hole, the passage of time itself slows relative to the outer regions. This effect, predicted by general relativity and confirmed by observation, is imperceptible on human scales but real. A clock placed close to the black hole would tick more slowly than one in intergalactic space. Light escaping from this region loses energy, its wavelength stretched into the red by gravity's pull. The faint glow that reaches us from the inner core has therefore been altered by its journey outward, carrying within it the subtle mark of curved space-time. In this sense, gravity not only defines motion, but sculpts the very fabric through which light travels. The balance achieved within Holmberg 15A is delicate yet enduring. Every particle of matter, from the smallest dust grain to the most massive star, contributes to the total gravitational field, while simultaneously responding to it. The system has reached a state where its components move not chaotically, but statistically stable, each one reinforcing the collective equilibrium. Over immense timescales, this balance can shift slightly as stars age and die, as black holes merge, or as the cluster itself evolves. Yet the essential structure remains. The galaxy has become an almost perfect gravitational organism, its form and motion aligned through time. The central black hole, though unseen, rules this organism with silent authority. Its gravity extends outward, far beyond the event horizon, controlling the orbits of millions of nearby stars. Occasionally, a wandering star or remnant passes too close, drawn into the zone of no return. As it falls inward, the star is torn apart by tidal forces, its material heated to extreme temperatures before vanishing. Such events are rare but not unknown. They release flares of radiation that briefly awaken the core, sending ripples through the surrounding gas. Even these outbursts, however, are contained by gravity, their energy absorbed and redistributed until the galaxy returns to quiet. The cycle of capture and calm is part of the natural rhythm of this dominion, a reminder that stillness does not mean inactivity. On larger scales, the gravitational power of Holmberg 15A contributes to the cohesion of the entire Abel 85 cluster. Its mass forms the anchor point around which smaller galaxies orbit, binding the cluster's structure against the expansion of space. Without such a core, the system might drift apart, but with it, the cluster endures as a gravitational family. Each member moves in relation to the central field, its orbit determined by the combined influence of the cluster's dark matter halo and the visible giants within it. The weight of Holmberg 15A stabilizes the entire ensemble, giving the cluster a center of gravity in both the literal and structural sense. Seen from our distant vantage, this gravitational dominion is invisible yet unmistakable. The galaxy glows faintly in optical light, but its true nature lies in what cannot be seen: the curvature of space, the binding of motion, the compression of gas, and the slow bending of time. Holmberg 15A is a portrait of gravity in its purest form, stripped of the drama of formation, reduced to balance and control. Every photon escaping its core, every star circling its unseen heart, every atom of gas drifting through its halo testifies to the same principle, that in the deep architecture of the universe, gravity is not only the builder but the keeper. Within this colossal equilibrium, Holmberg 15A endures the calm sovereign of its cluster, a dominion not of light, but of gravity, infinite, patient, and absolute. At the core of Holmberg 15A lies a black hole so massive that its influence extends across thousands of light years, an invisible anchor of the galaxy and the cluster around it. For much of astronomical history, such an object existed only as theory, a mathematical consequence of general relativity. Yet the evidence now gathered leaves little doubt. Every measurement of stellar velocity, every trace of curved light, and every whisper of faint radiation points to a single overwhelming presence. It is the largest known component of the galaxy, but it emits no light, shines with no reflection, and reveals itself only by what it does to its surroundings. If all the visible matter of Holmberg 15A were to vanish, this black hole would still define its structure, holding in gravity what it cannot hold in light. Its mass is estimated to exceed 40 billion suns, a figure so vast that it challenges both understanding and theory. Even among the largest known black holes, those at the hearts of quasars and giant ellipticals, this one stands near the upper limit of possibility. The detection of such a colossal object depends on indirect signs. Astronomers cannot see the event horizon; it is far too small and distant. Instead, they map the motions of nearby stars and gas using their speeds and orbits as traces of the gravitational field. In Holmberg 15A, stars within the central few thousand light-years move with extraordinary velocity far beyond what the galaxy's stellar mass can explain. The pattern of motion matches what would occur if an immense compact mass were present at the center. By fitting models to the data, researchers derive the mass of the hidden object, arriving at numbers that defy easy comprehension. The uncertainties remain large, but the scale is unmistakable. Holmberg 15A's black hole is among the greatest concentrations of matter ever detected, a gravitational singularity that outweighs entire galaxies. This mass reshapes its surroundings. The sphere of influence, the region where the black hole's gravity dominates over the combined pull of surrounding stars, spans thousands of light years. Within it, the orbits of stars are tightly curved, their paths bending around an invisible focus. The central density of light decreases toward the middle, a sign that many stars have been ejected through gravitational encounters with the black hole. The result is a core that appears almost hollow, not in material but in brightness. This evacuated region, visible in deep images, is thought to be the legacy of repeated mergers between black holes from earlier galaxies. When these massive bodies coalesced, they flung nearby stars outward through slingshot effects, carving the wide core that remains today. Thus, even the structure of the galaxy's brightness profile speaks of the black hole's presence and its turbulent past. If the Milky Way's central black hole were compared to a mountain, Holmberg 15A's would be a continent. Its event horizon, the boundary beyond which nothing escapes, would be roughly the size of our solar system encompassing the orbit of Neptune. Yet despite its size, it is nearly invisible. No light escapes its gravity. No direct image can be formed at this distance. Its presence must be inferred from motion and energy. Occasionally matter strays too near a wandering star, a cloud of gas, and as it falls inward it is heated to millions of degrees, releasing a brief flare of radiation before disappearing. These events are rare, but they are the only visible expression of an otherwise silent force. Even when dormant, the black hole exerts its influence continuously, holding nearby stars in swift curved paths, maintaining the equilibrium of the entire central region. The origins of this black hole trace back to the galaxy's history of mergers. Each time Holmberg 15A absorbed another large system, their central black holes spiraled together and eventually combined. This process releases immense amounts of gravitational energy, emitted as ripples in space-time gravitational waves that travel across the universe. Although such waves are far too weak to detect from this distance, their existence is certain. Over billions of years, repeated mergers built the central object to its current scale. In that sense, the black hole is both a record and a relic of cosmic history, the condensed sum of countless encounters. Its growth ended when the galaxy's environment changed, when the available gas was consumed or expelled, and no further large galaxies remained nearby to merge. Since then, it has rested in near silence, a dormant titan sustained by inertia alone. Despite its dormancy, the black hole's effects extend far beyond its immediate vicinity. It shapes the dynamics of gas throughout the cluster, heating the surrounding medium and influencing the long-term evolution of the system. Models of cluster thermodynamics show that even brief periods of activity from such massive black holes can inject enough energy to alter the cooling rate of hot gas for hundreds of millions of years. In this way, the black hole acts as a thermostat for the entire environment, maintaining a delicate balance between radiation loss and gravitational heating. When active, it may have driven outflows that prevented new stars from forming. When quiet, it allows the gas to cool, gradually preserving the cluster's current equilibrium. Thus, even in silence, it remains the regulator of cosmic temperature and time. From the perspective of physics, the scale of this black hole pushes theory to its limits. General relativity describes its behavior precisely, yet the numbers involved approach extremes where even that framework begins to strain. The density near the event horizon is beyond any ordinary measure, the curvature of space-time nearly infinite. Quantum effects, though negligible for smaller black holes, may play a role here, but their nature remains uncertain. The combination of immense size and great age makes this object an ideal but unreachable laboratory for fundamental physics. Its very existence raises questions about how such enormous singularities form and whether there is an upper boundary to their mass. For now, it stands as a rare example of what the universe allows when given time enough to build without interference. Viewed through the lens of observation, the black hole is not an isolated object, but the keystone of a vast system. Without it, the galaxy's central structure would lack cohesion. The inner orbits would loosen, and the equilibrium between motion and gravity would shift. The stars themselves are evidence of its presence, their paths woven together by the same invisible field that defines the black hole's domain. Even far from the center, its effect persists, guiding the slow rotation of the halo and anchoring the cluster's overall mass distribution. It is not only the heart of Holmberg 15A, but the gravitational pivot of Able 85 itself, an unseen monarch around which the galaxies of the cluster revolve. In quiet observation, nothing about this power is apparent. The galaxy's core glows softly, its light undisturbed, its profile smooth. Yet within that calm, the black hole remains immense, silent, and absolute. It neither announces its presence nor alters its surroundings through violence. It simply exists, bending space and commanding time. Every photon escaping the galaxy has passed through its gravitational field, its path subtly curved, its frequency slightly redshifted by the depth of the potential well. The light that reaches us millions of years later carries those traces, a memory of curvature, an echo of unseen weight. Holmberg 15A's black hole is not an anomaly within it, but its defining essence, the invisible center of a galaxy built around absence, where the strongest force in the universe has reached its most perfect stillness. The space surrounding the central black hole of Holmberg 15A marks the threshold between the visible and the invisible, a region where the last traces of light fight against gravity before surrendering. Though the core appears calm from afar, the physics unfolding in its inner zones are among the most extreme in the universe. Here matter spirals inward on unstable orbits, drawn by the immense pull of the central mass. As it approaches the event horizon, its motion accelerates to a significant fraction of the speed of light, generating intense heat and radiation. Yet because Holmberg 15A's black hole is so enormous, the infalling material glows faintly compared to smaller, more active galactic nuclei. The energy is spread across vast distances, diluted by scale, and much of it is trapped by gravity itself. What escapes does so softly, a low whisper of X-rays and radio waves marking the boundary where light and darkness exchange dominion. This region, known as the accretion zone, is the meeting place of energy and gravity. It begins far from the event horizon, where clouds of gas and dust drift through the gravitational field. As these clouds lose angular momentum, they form a disk of orbiting material that gradually spirals inward. Friction between particles heats the disk to millions of degrees, causing it to radiate across the electromagnetic spectrum. In the early life of the galaxy, when mergers were frequent and gas abundant, this process would have blazed brilliantly, turning Holmberg 15A into a quasar-like beacon visible across cosmic distances. But now the supply of cold gas has long since vanished, either consumed by star formation or expelled during ancient outbursts. What remains is a faint echo of that fiery past, a quiet, stable system, where accretion proceeds at a slow and intermittent pace. The few photons that escape from near the event horizon carry information about this process. Some travel outward along paths bent by gravity, emerging as weak X-ray flares detectable by space telescopes. Others follow more circuitous routes, looping through warped space, before escaping their wavelength stretched into the radio band. The result is a spectrum of gentle emission dominated by synchrotron radiation from electrons spiraling along magnetic fields. These emissions, though faint, are critical clues. They reveal that the black hole is not entirely silent, but breathes in slow rhythm, occasionally drawing in stray matter that stumbles too close. Each episode releases a short pulse of light, an invisible heartbeat at the scale of galaxies. Closer still, the effects of relativity become dominant. Space near the event horizon is curved so deeply that time itself runs slower relative to the outer world. To a distant observer, matter falling toward the black hole appears to move ever more slowly, fading and redshifting as it approaches the horizon, until it seems to freeze in place. Yet from the perspective of the infalling material, the journey ends quickly, time compressing into a brief descent. This duality of motion and stillness, of brightness and disappearance, defines the physics of the inner core. Light emitted near the black hole is both delayed and distorted, creating an apparent halo that outlines the region of no return. Though too distant to resolve directly, theoretical models and analogies from other systems suggest that Holmberg 15A's central region would exhibit the same glowing boundary, a faint circular silhouette where gravity traps most radiation and allows only a portion to escape. The interplay of gravity and light near the event horizon also influences the surrounding galaxy. As the accretion flow shifts and cools, magnetic fields twist and reconnect, occasionally launching weak outflows or jets that extend thousands of light-years into space. In Holmberg 15A, remnants of these events are seen in faint radio lobes, long silent structures filled with relativistic particles from ancient eruptions. They stand as fossilized evidence of a time when the black hole was active, when energy poured outward even as matter fell inward. Today these lobes persist only as faint ghosts, their glow powered by the slow decay of magnetic fields. Yet they demonstrate that even in stillness, the core retains the memory of motion, that the quiet now observed is the product of exhaustion, not emptiness. The boundary between light and darkness is also the boundary between knowledge and mystery. Physics can describe what happens outside the event horizon with great accuracy, but inside it known laws break down. Space and time exchange roles, and the singularity at the center, if it exists as predicted, represents a point where density becomes infinite. For an object as massive as the one in Holmberg 15, the curvature of spacetime at this point is unimaginable. Yet this extreme gravity is hidden from view, shielded by the event horizon, ensuring that no signal can reveal what truly happens beyond. All that can be known is inferred from the behavior of matter at the edge, where the universe allows us to see its own limits. The black hole thus becomes both an object and a frontier, a place where observation reaches its end, and theory must take over. For astronomers, studying such massive black holes offers insight into how galaxies and clusters evolve. The correlation between black hole mass and the velocity dispersion of stars, known as the M-sigma relation, suggests a deep connection between the growth of the central black hole and the formation of the galaxy around it. Holmberg 15A, with its exceptional mass, sits at the extreme end of this relation, providing a rare case study of what happens when both galaxy and black hole grow unchecked. Its enormous scale indicates that feedback processes the outflows, and radiation that usually limit growth may have been weaker here or balanced differently. The result is a system where gravity dominated, completely consuming all available fuel until equilibrium was reached. Light emerging from the inner regions of Holmberg 15A carries the marks of that equilibrium. Each photon escaping the gravitational well loses a tiny fraction of its energy, emerging redder and cooler than when it was emitted. The combined effect is subtle but cumulative, giving the core's light its distinctive softness. When observed from Earth, this gentle gradient disguises the violence of the physics behind it. The calm surface we see a smooth glow fading into the halo is the visible expression of an invisible process, the continual exchange of energy between matter motion and gravity at the edge of darkness. Even at such distances, the light retains its coherence. It travels for hundreds of millions of years through intergalactic space unimpeded by dust or gas until it reaches our telescopes. The photons that arrive are ancient, yet they still encode the curvature of the space they left behind. Their paths were bent, their frequencies stretched, but their origin remains clear. They come from the borderland where light surrenders to gravity, where the laws of the universe balance on a knife's edge between existence and erasure. To observe them is to glimpse not the black hole itself, but the threshold that defines it, the final delicate boundary where the visible cosmos ends and the unseen begins. Holmberg 15A's core embodies that frontier, immense, silent and eternal, the place where light is forever drawn inward, yet never fully lost. Although Holmberg 15A appears tranquil in visible light, faint traces across other wavelengths reveal that the colossal black hole at its centre has not always been silent. The enormous gravity that governs the galaxy also drives processes that release energy back into space, slow winds of plasma relic jets from ancient outbursts and diffuse radio lobes marking the memory of a once active core. In the distant past, when gas was more abundant, matter falling toward the black hole would have ignited a powerful accretion flow. As material spiraled inward, it compressed heated and twisted magnetic fields, converting gravitational energy into motion and radiation. Some of that energy was directed outward along the poles, forming twin jets that pierced the surrounding gas and extended far beyond the visible body of the galaxy. Today those jets are gone, but their remnants persist as radio echoes faint lobes stretching across intergalactic space, like the faded outlines of a storm long past. These radio lobes, detected by sensitive arrays on Earth and in orbit, still carry the faint glow of synchrotron radiation light emitted by high-energy electrons spiraling around magnetic field lines at nearly the speed of light. Their shapes are irregular, diffused by time, their brightness uneven. By studying their morphology, astronomers reconstruct the sequence of events that created them. The alignment of the lobes suggests they were produced during multiple episodes of activity, each lasting millions of years. Between these eruptions, the central black hole likely entered periods of quiet accreting slowly, before reigniting as new material became available. Such cycles are common in massive galaxies, but in Holmberg 15A the scale is amplified by the sheer size of its central engine. Each burst of activity would have released energy equivalent to the combined output of trillions of stars, enough to reshape the surrounding gas and influence the entire cluster. The interaction between these outflows and the intracluster medium is visible in X-ray observations. Around the galaxy's centre, subtle cavities appear within the hot gas depressions, where radio lobes once expanded, displacing the surrounding plasma. These cavities, now partly refilled, mark the footprints of past jets. Their symmetry and distance from the core allow scientists to estimate the energy released and the timescale of each event. In Holmberg 15A, these cavities extend tens of thousands of light years and may be hundreds of millions of years old. The energy required to create them is immense, yet consistent with what a black hole of such mass could produce. Even in its quiet state, the central engine of the galaxy retains the capacity to influence the structure and temperature of the cluster around it. The calm we see today is the residue of balance restored after extraordinary events. The mechanics of jet formation begin near the black hole's event horizon. Within the accretion disk, magnetic fields twist under the combined effects of rotation and inflow. These fields can channel energy outward, forming collimated streams of plasma that escape along the spin axis of the black hole. In powerful quasars, such jets can extend for millions of light years, but in galaxies like Holmberg 15A, where the accretion rate is low, they appear weaker and slower. Over time, however, even faint jets can carve vast cavities in the surrounding gas, heating it and slowing the cooling process that might otherwise feed new star formation. This self-regulating cycle is known as feedback. The black hole consumes, radiates, and expels, shaping its environment while controlling its own growth. Holmberg 15A in its present mature state is the product of such feedback loops repeated over billions of years, each outburst bringing it closer to equilibrium. The last major period of activity likely occurred hundreds of millions of years ago. The radio lobes, now dim and extended, indicate a source that has been fading for ages. The energy stored within them continues to dissipate as electrons lose momentum and magnetic fields weaken. Eventually, these lobes will vanish entirely, their particles merging with the intra-cluster gas, their shapes erased. Yet even as they fade, they continue to affect the environment. The energy they once delivered remains distributed through the hot plasma of the cluster, maintaining temperatures that prevent rapid cooling and condensation. In this way, relic jets act as long-term stabilizers of the system echoes that still perform a function after their source has gone silent. For observers on Earth, the faint radio signals from Holmberg 15A are measured at frequencies too low to be seen directly, but can be translated into maps of emission. These maps reveal diffuse lobes stretching symmetrically from the core, their edges blurred by diffusion. The central region shows only a weak point source consistent with a black hole that now accretes at a fraction of its potential rate. The overall radio power places Holmberg 15A in the category of low-excitation radio galaxies systems, where the central engine operates in a maintenance mode, producing enough energy to sustain equilibrium, but not enough to create luminous jets or bright emission lines. In optical wavelengths, the galaxy appears inert, but radio observations uncover its hidden vitality, proving that even in stillness, processes of motion and exchange continue. These faint signatures are more than relics. They form part of the long narrative connecting galaxy and black hole. Every burst of energy that once erupted from the core has left an imprint on the cluster's structure. Over time, the repetition of such outflows has created a dynamic balance. Gas cools toward the center, feeds the black hole and triggers new activity, which then reheats and redistributes the gas, halting further infall. The result is a self-regulating system that can persist for billions of years. Holmberg 15A represents the late stage of this cycle, where energy input and loss are almost perfectly matched, creating the appearance of timeless calm. Beneath that calm, however, gravity and energy continue their endless dialogue, maintaining the fragile balance that defines the cluster's present state. The history recorded in the radio echoes of Holmberg 15A offers clues to the evolution of galaxies across cosmic time. Similar processes operate in other giant ellipticals at the centers of clusters, but few show such an extended and faintly preserved pattern of activity. The scale of the lobes, the symmetry of the cavities and the quiet of the core together illustrate the life cycle of a galactic nucleus ignition, expansion, dissipation, and rest. Each stage leaves traces detectable in a different wavelength X-rays for heat radio, for electrons, optical light for the stars that bear witness. In combining these views, astronomers reconstruct a picture of continuity rather than crisis, a system that changes slowly but never truly stops. Seen from the perspective of time, these jets and winds are brief events, momentary flickers in the life of a galaxy that endures for tens of billions of years. Yet their cumulative effect is profound. They determine how stars form, how gas moves, and how light travels through the cluster. They shape not only the galaxy's future, but the temperature and density of the space surrounding it. In this sense, Holmberg 15A is not just a passive structure shaped by gravity. It is an active participant in the evolution of its environment. The faint radio echoes that reach our instruments are the last evidence of that participation, the lingering sound of energy once released still fading into the silence of intergalactic space. At this stage of its existence, Holmberg 15A rests in near-perfect balance. The black hole at its centre consumes, little emits little, and disturbs nothing. Yet the memory of its earlier vigour remains etched in the faintest frequencies of the cosmos. These residual signals travelling through space for hundreds of millions of years remind us that even the most tranquil objects are born of turbulence. What we see as serenity is merely the latest chapter in a story written by energy and gravity, a story whose echoes still drift outward, quiet but unending across the vast expanse of the cluster's dark and ancient air. Understanding the scale of Holmberg 15A requires more than observation. It requires inference, mathematics, and patience. Its light alone cannot reveal its full nature, for most of its mass is hidden either in dark matter that emits no radiation, or in a black hole that swallows all that approaches. To measure something so elusive, astronomers turn to the only evidence gravity provides motion. Every orbit, every tilt of starlight, every distortion in the surrounding gas acts as a signature of the unseen. By mapping how matter moves under gravity's control, scientists reconstruct the invisible architecture that gives the galaxy its shape. In the case of Holmberg 15A, those motions describe a system of extraordinary weight, far exceeding what its faint luminosity would suggest. The galaxy's surface brightness is low, but its gravitational pull is immense, proving that mass not light is its defining property. The process of weighing a galaxy begins with its stars. Spectroscopy allows astronomers to measure the Doppler shifts in their light, revealing their velocities along the line of sight. In elliptical galaxies where stars move randomly, rather than in ordered rotation, this motion appears as a broadening of spectral lines. The greater the spread, the faster the stars move, and the deeper the gravitational potential must be to keep them bound. In Holmberg 15A, the dispersion of velocities reaches extraordinary levels, indicating that the stars are racing through space at hundreds of kilometers per second. These measurements, combined with models of the galaxy's light distribution, yield an estimate of the total mass enclosed within any given radius. The results show that the mass increases smoothly from the outskirts inward, culminating in a core whose density is dominated by the central black hole. But stars alone cannot account for all of the observed motion. Beyond a certain radius, the velocities of stars and hot gas remain high, even where visible matter becomes scarce. This discrepancy points to the presence of dark matter, a substance that does not emit or absorb light, yet exerts gravitational influence. In Holmberg 15A, dark matter forms a vast invisible halo surrounding the luminous body, extending far beyond what telescopes can directly observe. Its mass outweighs the combined total of all stars and gas in the galaxy, anchoring both the system itself and the larger cluster around it. The dark halo ensures that the outermost stars remain bound, preventing the slow disintegration that would otherwise occur over billions of years. Without it, the galaxy's faint edges would drift away into intergalactic space. Measuring this invisible halo requires more than stellar velocities. Astronomers also use X-ray observations of the hot intracluster gas that fills the region. This gas trapped by the galaxy's gravity settles into hydrostatic equilibrium, a balance between pressure and weight. By mapping its temperature and density, scientists can infer the gravitational field needed to hold it in place. In Holmberg 15A, the data confirm an extraordinarily deep potential well extending into the surrounding cluster. The gas temperature rises toward the center, peaking where the black hole's influence becomes dominant. From these patterns, the total mass of the system can be reconstructed, revealing the smooth transition from the galaxy's inner regions to the cluster's outer domain. Holmberg 15A is not only the center of light within Abell 85, but also the anchor of its gravitational balance. lensing provides another way to weigh what cannot be seen. When light from distant galaxies passes behind a Bell 85, it bends under the influence of gravity, forming arcs and distortions in the background field. By measuring these distortions, astronomers can map the distribution of mass throughout the cluster. Holmberg 15A sits precisely at the region of strongest lensing, the deepest part of the gravitational potential. The curvature of space here is gentle but measurable, a direct expression of Einstein's theory in action. Even at such distances, the bending of light confirms the extraordinary weight of the galaxy and its dark halo. Each warped image of a background galaxy becomes a data point adding to the map of the unseen. Together, these methods converge on the same conclusion. Holmberg 15A is one of the most massive galaxies ever measured, a structure where light is merely an afterthought to gravity. Weighing the invisible also means acknowledging uncertainty. The precision of these methods depends on assumptions about the shape of the galaxy, the orbital patterns of its stars, and the physics of the surrounding gas. Yet even within these limits, the results remain consistent. Whether measured through stellar motion, X-ray temperature, or gravitational lensing, the mass of Holmberg 15A falls within the same extraordinary range. It rivals or exceeds the combined mass of several Milky Way galaxies concentrated into a single diffuse sphere. The central black hole alone may account for a significant fraction of this total, a proportion unprecedented among galaxies. This ratio challenges existing models of how galaxies and black holes co-evolve. In most systems, the central object contributes only a small part of the total mass. In Holmberg 15A, it approaches equality, suggesting a history dominated by mergers of giants rather than gradual growth. These measurements also reveal something about time. The mass of the galaxy, its gravitational field, and the distribution of stars together define a system that evolves slowly, if at all. Dynamical relaxation, the process by which stellar motions average out irregularities, occurs over timescales longer than the age of the universe. As a result, the structure of Holmberg 15A is essentially frozen, preserved in a state of near-perfect equilibrium. Each star follows its orbit through a potential that will change only imperceptibly over billions of years. Even the cluster around it, vast and diffuse, remains bound by the same invisible framework. The weight of the unseen holds not just matter, but time itself, fixing the rhythm of cosmic evolution into an enduring stillness. This stillness is deceptive. Gravity, though quiet, is never inactive. Every orbit, every vibration in the intracluster gas, every fluctuation in dark matter density reflects a continuous exchange of energy. On the smallest scales, stars interact gravitationally, their collective behavior smoothing over chaos. On the largest, the cluster's mass distribution subtly shifts as galaxies move and dark matter flows. But these changes are so slow that no telescope will ever record them directly. The galaxy appears timeless because the forces shaping it act on intervals that exceed all human measure. To weigh such a system is to glimpse a frozen moment in an ongoing process, one that has been unfolding since the universe was young and will continue long after it fades. The instruments that make these measurements are extensions of human patience, telescopes that collect light over hours, days, and years to reveal motion too faint to see. Each photon gathered contributes to the map of gravity's design. The combination of these data produces not just a number, but a narrative, a story of matter, drawn together of light, bent by curvature of equilibrium maintained by invisible weight. Holmberg 15A's enormity is not expressed through brightness, but through persistence. Its gravity is the quiet handwriting of the cosmos traced through stars and gas and the very shape of space. To weigh it is to read that script, to understand that even in darkness, the universe records its own history through the motion of the things it holds. In the end, the measure of Holmberg 15A is not a single value but a realization that what we see is only the thinnest layer of what exists. Beneath the faint glow of its stars lies a mass that cannot be touched or seen, only inferred through its pull. The galaxy endures as a reminder that the universe is built not from light, but from gravity's invisible architecture. Each orbit within it is a proof of presence, each arc of distorted light a confirmation of weight. Holmberg 15A is the embodiment of what it means to measure the unseen, a monument to forces that reveal themselves only through motion silent yet absolute, shaping the cosmos in the language of the invisible. Among all the galaxies ever measured, Holmberg 15A stands near the upper boundary of possibility, a system so vast and massive that it challenges our understanding of cosmic growth. When its central black hole was first estimated to weigh tens of billions of solar masses, it immediately entered the realm of the extraordinary. Few other objects approach such scale. The black hole in Messier 87, famous for being imaged directly, holds around 6.5 billion solar masses. The one in NGC 4E89, another giant elliptical, reaches perhaps 21 billion. Yet Holmberg 15A's core surpasses them, positioning it among the largest gravitational structures known to exist. Even in a universe that routinely produces extremes, this galaxy remains an outlier, a colossus among giants whose existence raises questions about how far gravity and time can build before limits intervene. Its exceptional size is not a coincidence, but a natural result of its environment. Holmberg 15A resides at the center of the Abel 85 cluster, where galaxies have been converging for billions of years. Each infell, each merger, each slow absorption of smaller systems has added to its mass. Unlike isolated galaxies, which may experience long periods of relative quiet, central ellipticals in rich clusters grow continuously as surrounding members drift inward. The cluster's gravity acts like a funnel channeling matter toward its core where it joins the central galaxy. Over cosmic time, this process amplifies differences, making the largest ever larger and the small ever smaller. The result is a hierarchy of scale that culminates in galaxies like Holmberg 15A, whose sheer mass transforms them from participants in the cluster to rulers of it. The scale of this galaxy can be appreciated only in comparison. If the Milky Way were placed within Holmberg 15A, it would disappear entirely within its inner halo. Our solar system, positioned near the center of its luminous body, would be surrounded by stars so distant from one another that even their collective light would form only a faint glow. The galaxy's radius extends hundreds of thousands of light years, and its gravitational influence stretches far beyond that. Its total mass, including dark matter, likely exceeds 10 trillion solar masses, enough to dominate the dynamics of an entire region of space. Yet despite this immensity, its brightness is low spread thinly across a vast area. It is a paradox of the universe that its largest objects are often its faintest. For astronomers, studying such an extreme system offers both a challenge and an opportunity. The standard models of galaxy formation explain how black holes and galaxies grow together with feedback from accretion-limiting runaway growth. But Holmberg 15A may have escaped this regulation. Its enormous central mass implies that mergers played a greater role than internal processes. Each major collision added both stars and central black holes, producing a chain of growth that compounded over time. Because the galaxy now resides in a relatively gas-poor environment, further growth through accretion has nearly ceased locking it in its current state, an immense relic from an earlier, more chaotic era. To observe it, is to see what happens when cosmic building continues without interruption until the supply of material is exhausted. The existence of such a system challenges the scaling relations that link black hole mass to host galaxy properties. In most galaxies, the central black hole accounts for less than 1% of the total stellar mass. In Holmberg 15A, that proportion may be closer to 10% or even more, breaking the pattern observed elsewhere. This suggests that feedback mechanisms, which usually prevent excessive black hole growth by heating and expelling gas, may have failed or been bypassed here. Perhaps the cluster environment provided a constant influx of material that overwhelmed any self-regulation. Perhaps the mergers occurred so rapidly that the usual checks could not operate. Whatever the reason, the result is a galaxy that redefines the limits of the known correlation, an outlier so large that it forces theory to expand to include it. Comparisons to other extreme systems highlight its uniqueness. TON 618, the luminous quasar whose central black hole may reach 66 billion solar masses, represents an active phase in the early universe when gas was plentiful and black holes grew rapidly through accretion. Holmberg 15A, by contrast, is an old system, its activity long past. It demonstrates that even after the quasar era ended, mergers continue to shape the cosmic landscape, building immense but faint remnants. Where TON 618 blazes with radiation, Holmberg 15A whispers with gravity. Both embody extremes of the same process, one in light, the other in stillness. Together they outline the range of what the universe can produce from bright youth to quiet age. The study of such massive systems also informs our understanding of the largest structures in existence, clusters, filaments, and the cosmic web itself. Central galaxies like Holmberg 15A serve as the gravitational anchors of these vast networks. They collect mass-stabilized cluster dynamics and influence the thermal balance of the intergalactic medium. Without them, the delicate equilibrium between collapse and expansion would falter. In this sense, Holmberg 15A is not just an anomaly, but a cornerstone of cosmic architecture. Its existence helps maintain the stability of its cluster, shaping the orbits of neighboring galaxies and moderating the temperature of the surrounding gas. Its gravity binds, its history instructs, and its stillness sustains. Yet for all its mass, the galaxy is nearly invisible to casual observation. Even powerful telescopes require long exposures to distinguish its diffuse edges from the background. Its faint light deceives the eye, concealing a gravitational strength that rivals entire clusters. This contrast between appearance and substance makes Holmberg 15A a kind of cosmic paradox, an immense structure hidden in plain sight. To study it is to confront the difference between what the universe shows and what it is. Brightness, which so often defines importance in astronomy, becomes irrelevant here. The true measure of significance lies not in light but in weight, not in visibility but in endurance. As technology improves, the precision with which astronomers can probe such giants increases. Instruments capable of detecting gravitational waves from supermassive black hole mergers may one day capture the faint echo of events that shaped Holmberg 15A. Future space observatories may detect the residual heat or faint jets that mark continuing accretion. Each new observation will refine our understanding of how such extremes are reached and what physical laws might limit them. For now, the galaxy remains a record, a quiet ledger written in stars and gravity, preserving the sum of countless cosmic transactions. Holmberg 15A's place among known galaxies is therefore more than a statistic. It is a reminder of scale itself. Its mass, its age, and its isolation demonstrate what the universe can create when given time and matter in abundance. It stands at the edge of what is possible, not because it defies physics, but because it fulfills it to completion, In the spectrum of galactic evolution, it is the endpoint, the fully grown form of a process that began when the first small galaxies gathered from the primordial gas. To look at it now is to see cosmic maturity, the long equilibrium that follows creation's fever. The record it holds is not only of its own enormity, but of the universe's capacity to build and preserve order across incomprehensible distances. Holmberg 15A is the colossus that measures the possible, the monument that marks how far gravity can go before silence takes over. In the long arc of cosmic time, Holmberg 15A has entered a stage of profound stillness. The great collisions that built it have ceased. The flows of gas that once ignited star formation are exhausted, and its central black hole has grown too massive to be easily disturbed. What remains is a galaxy in equilibrium, an immense system sustained by the momentum of its stars and the deep gravity of its core. It shines softly with the diffuse light of old suns whose fuel burns slowly but persistently. There are no bursts, no new clusters, no spiral arms glowing with youth. The processes that once shaped it have quieted into stability. In this calm, the galaxy endures its fate, unfolding not through drama, but through the slow work of time itself. This phase is the natural outcome of a long history. Every merger, every accretion event, every outflow of energy from the central black hole has brought Holmberg 15A closer to stasis. The violent epoch that defined its growth has given way to the steady aging of its stellar population. Most of its stars are now small, red and ancient, burning their remaining hydrogen, with efficiency but little brightness. The massive blue stars that once illuminated its mergers are long gone, their supernovae having seeded the cluster with heavy elements. The interstellar medium, once dense and turbulent, has thinned into a tenuous mist of hot plasma. In X-ray light, this gas glows faintly, filling the central region of the cluster with a soft halo that testifies to both past violence and present calm. The conditions for new stars are absent. Gravity and temperature together maintain a balance that prevents cooling, ensuring that the galaxy's population will only age further. The future of such a system unfolds on timescales that defy ordinary comprehension. Over the next tens of billions of years, the brightest stars will fade, leaving behind long-lived red dwarfs and stellar remnants, white dwarfs, neutron stars and black holes. These remnants will orbit the galactic core like embers in cooling air, their light weak but enduring. The galaxy's luminosity will gradually decline, though its mass will remain almost unchanged. Even as the last visible stars dim, the gravitational field will persist unaltered by the loss of radiance. The structure will remain intact, held together by gravity's unrelenting pull. To an observer in that distant future, Holmberg 15A will appear as a faint smear of ancient light, the echo of a cluster long past its prime. Within the cluster, smaller galaxies continue their slow inward drift, but most are now too distant to merge within the universe's current age. The space between them expands under cosmic acceleration, counteracting gravity's pull. Holmberg 15A, though massive, cannot capture what recedes faster than light can cross. The cluster as a whole will gradually loosen its members, drifting apart as the expansion of the universe overcomes their mutual attraction. Only those galaxies already bound will remain. In time, Arbol 85 will contract into a single massive system, a remnant cluster dominated by Holmberg 15A, surrounded by the diffuse remnants of its neighbours. It will become an island of matter, adrift in the dark, self-contained and isolated, a monument to a universe that once teemed with interaction. As the surrounding cosmos continues to expand, galaxies will slip beyond the observable horizon, their light stretched into invisibility by the redshift of accelerating space. For future observers within Holmberg 15A, the universe will grow emptier. The familiar constellations will fade, the cosmic background radiation will cool to undetectable levels, and only the internal stars of the galaxy will remain visible. The night sky will contract into a single glowing structure, the last record of a once connected cosmos. In that distant epoch, the inhabitants of this galaxy, if any exist, would see only the faint glow of their own cluster and might never know of the wider universe beyond it. The vast isolation that defines the cosmic future will find its quiet center here where gravity holds, but expansion prevails everywhere else. Within the galaxy itself, slow changes will continue. Gravitational encounters between stars, though rare, will gradually alter orbits, transferring energy, and causing some stars to drift outward, while others fall inward. Over unimaginably long timescales, this process of relaxation will flatten gradients and spread stars evenly through the potential well. Some may be ejected entirely, gaining enough velocity to escape into intergalactic space. Others will spiral toward the central black hole, their mass adding incrementally to its total. Yet these processes occur over intervals so vast that the galaxy's overall form will remain effectively unchanged for trillions of years. The calm visible today will endure almost indefinitely, a stability born of exhaustion rather than peace. The black hole at the center will also persist, though its role will evolve. With little new matter to consume, it will remain dormant, influencing the galaxy only through its gravity. On even longer timescales, it may begin to lose mass through the slow evaporation predicted by quantum theory. This process, known as Hawking radiation, is exceedingly weak for an object of such mass. It would take more than 100 quintillion years to make a measurable difference. Still, the concept underscores the ultimate impermanence of even the most enduring structures. Nothing, not even a black hole of 40 billion suns, lasts forever. The fate of Holmberg 15A, like that of all galaxies, is not destruction but gradual fading, the slow dispersal of light, and the retreat of energy into silence. To contemplate that future is to witness the universe moving toward simplicity. The complexity of the early cosmos, the star formation, the mergers, the bursts of radiation gives way to a state defined by stillness. Energy becomes evenly distributed and temperature differences fade. Galaxies like Holmberg 15A, having completed their growth, serve as the intermediaries between creation and quiet. They are the bridges from the dynamic to the static, from the luminous to the dark. In their vast calm, they hold the memory of everything that came before, the collisions that built them, the fires that illuminated them, and the forces that now preserve them. Their fate is not tragic but inevitable, the natural conclusion of processes that began with the first atoms of matter. Even now, as telescopes on Earth capture its faint light, Holmberg 15A exists mostly as a record of time. The photons that reach us left hundreds of millions of years ago, during an era when the galaxy was slightly younger but already mature. What we see is not its present but its past, and even that is a fragment of a much longer continuum. In reality, it has already advanced further into stillness, its stars slightly dimmer, its halo a bit more diffuse. By the time its light reaches us again, the universe will have changed beyond recognition. This gap between what is and what is seen adds to the sense of timelessness that defines such systems. Observing Holmberg 15A is like reading a letter sent from an age when the universe breathed more deeply, its matter still moving toward balance. The quiet fate of this giant galaxy is not an end but an equilibrium. It will remain long after more active systems have faded its gravitational field, enduring as a stable remnant of cosmic architecture. Over the ages, its stars will cool, its glow will dim, and its role as a hub of interaction will cease, yet its structure will persist, the gravitational skeleton of what was once a living cluster. Holmberg 15A's destiny is to outlast the noise of creation, to survive in silence as the cosmos thins around it. It stands as both a relic and a preview of what awaits all galaxies, the transition from energy to inertia, from brightness to endurance, from motion to calm. Its stillness is not absence, but completion, the universe at last at rest. The light that leaves Holmberg 15A begins a journey across 700 million years of space and time before reaching our eyes, carrying the record of a galaxy already ancient when it departed. Every photon that arrives today was released by a star that has since drifted along its orbit, perhaps slightly dimmer, perhaps already gone. To see this galaxy is to look backward across a gulf so vast that time itself becomes part of the image. The universe through which that light travels is not static. It stretches as it expands, and the light stretches with it, its wavelengths lengthened into red by the swelling of space. By the time it reaches us, it carries both the glow of distant matter and the signature of cosmic growth. Holmberg 15A, immense and nearly motionless within its cluster, becomes a kind of clock, a marker, by which we measure not only distance but duration. In astronomical terms, 700 million years is only an instant compared to the galaxy's true age, yet, within that interval, entire histories on Earth have unfolded. The photons now entering telescopes left when our planet's continents were still shifting toward their present positions, and when the first complex life was emerging from the oceans. Since then, human civilizations have risen evolved instruments to measure light, and turned those instruments outward to intercept signals that began their journey before humanity existed. Each observation is therefore an intersection between two vastly different timescales, the slow rhythm of galaxies and the quick pulse of human awareness. The act of studying Holmberg 15A unites these tempos, allowing us to glimpse the past of another world while standing in the present of our own. The concept of time beyond light applies not only to distance but to perspective. The galaxy we see is frozen in a moment of its own history, one that will never change for us. No matter how long we watch, the photons that reach us will always come from that same ancient epoch. In this way, observation becomes an encounter with permanence, yet within that still image lies the knowledge of motion stars, orbiting gas, drifting dark matter, flowing processes that continue unseen. The light is static, but the reality it represents is dynamic. To look at Holmberg 15A is to hold a still photograph of something alive, to witness a motion that time and distance have slowed to immobility. The paradox deepens the sense of calm that defines this system movement, so vast and slow that across human ages it appears as rest. Light itself plays a central role in how we understand such distant structures. It is both messenger and measurement, carrying the information we need to reconstruct physical conditions we can never touch. The intensity of starlight reveals how densely stars are packed. Its colour shows their temperature and age. Its spectrum encodes the chemistry of the galaxy and the motions of its components. Yet light is fragile, shaped by everything it encounters. As it leaves the galaxy, it is altered by gravity, stretched by expansion and dimmed by distance. The faint beam that reaches our telescopes is therefore not pure, but translated the result of a long negotiation between matter and space. Each photon is a survivor, carrying within its energy the memory of every gravitational well and void it crossed. When it finally reaches us, it brings the universe's handwriting written in light. Through such signals, astronomers reconstruct the galaxy's past. The redshift of its light fixes its distance. The absorption lines reveal the elements forged in its stars. The smoothness of its spectrum confirms its age. Every detail extracted from the faint glow adds another layer to the picture, an ancient cluster, a colossal elliptical at its heart, a black hole dominating the centre, and a halo fading into darkness. From these fragments of information, a coherent image emerges, one that stretches across space and time to connect the distant and the immediate. In this way, the study of Holmberg 15A becomes not merely an exercise in measurement, but a meditation on duration. The light we capture is ancient, but its meaning is always renewed with each observation. Over the coming billions of years, the light from Holmberg 15A will continue to travel outward, passing through regions of space that will themselves change. The universe's expansion will carry it into colder, thinner domains, where the background radiation fades and matter becomes sparse. Future observers in distant galaxies, if any remain, will see its glow increasingly redshifted, its energy spread thin by the stretching of space. Eventually its photons will lengthen into wavelengths too long for detection by any conceivable instrument. At that point, the light of Holmberg 15A will effectively vanish from the universe's visible record, not extinguished, but dispersed, transformed from radiance into the faint rhythm of cosmic background. In that remote epoch, the galaxy will still exist, but its presence will no longer be knowable through light. It will have passed beyond observation, existing only in gravity's silent persistence. The inevitability of this fading underscores a broader truth about the cosmos. Every source of light, every star, every quasar, every galaxy participates in a cycle of appearance and disappearance governed by expansion. The speed of light sets a horizon to knowledge. Beyond a certain distance, objects recede faster than their signals can reach us. Holmberg 15A, though vast, is bound to this same fate. One day its image will slip beyond the horizon, its photons forever unable to bridge the widening gulf. When that moment comes, the record of its existence will persist only in the traces it has already sent, the ancient light now stored in our observatories, the data etched into instruments, and the understanding written into human thought. The universe will continue, but this particular conversation between light and mind will be complete. For now that conversation continues. The light from Holmberg 15A, collected by telescopes and processed by instruments, becomes the raw material for comprehension. Each observation refines our knowledge not only of the galaxy itself, but of the forces that govern all galaxies. The faintness of its glow, the breadth of its halo, and the gravity of its core together form a pattern repeated throughout the cosmos, scaled up to an extreme. By studying such systems, scientists trace the evolution of structure from the smallest clusters of stars to the largest networks of galaxies. Holmberg 15A is thus not an isolated curiosity, but a key to the universe's architecture, a single example of how matter arranges itself under the patient rule of gravity and time. The light that began its journey hundreds of millions of years ago will continue to arrive for as long as we have eyes to see it. Each photon is a message from a world that endures beyond our own time, a reminder that the universe is both transient and eternal. In the darkness between galaxies, light and gravity play their endless game, one escaping the other, pulling together, creating the patterns we call existence. Holmberg 15A embodies that balance, a structure vast enough to outlast change, luminous enough to be seen across eras, quiet enough to remind us that stillness is not void but continuation. Its glow is the voice of endurance, whispering across time that the universe remains, that gravity holds, and that even light, though finite, carries the story of forever.